Hello, this is Mr. Brooks and welcome to Lesson 7-2, Similar Polygons. In this lesson, we're going to identify similar polygons and we're going to apply similar polygons. Now, the first thing we need to learn is what does the word similar mean. If you remember back to congruent, it means congruent figures are same size, same shape. Well, similar means same shape, different size. The technical definition of similar would be corresponding angles congruent and corresponding sides proportional. The symbol for is similar to is the little squiggle that you put on top of the equal sign when we're saying is congruent to. So this sign right here means is similar to. When you're comparing similar figures, again, their angles are congruent, their sides are proportional. That proportion is called the similarity ratio. Let's look at example 1 and see what we're talking about. In example 1, they tell us ABCD is similar to, again, this is the symbol is similar to EFGH. So if we know that, again, similar means your angles are congruent, your sides are proportional. Well, if A is 53 and A corresponds to E, then the measure of angle E must also be 53 degrees. And if F is 127, then you know the measure of angle B has to be 127 degrees also. And since your consecutive angles are supplementary, you know both these figures are parallelograms. And so your opposite angles are congruent as well. In quick check number 1, not only do they ask us for the measure of angle B, which we just got to be 127, they're also asking us to fill in the blank for the proportion. It tells us segment GH over segment CD is going to equal FG over what segment? Please pause the video while you try to figure this out. Hopefully you decided that that would be over segment BC. In example 2, they're asking us to determine whether the triangles are similar, and if they are, to write a similarity statement and give the similarity ratio. Well, for us to figure out, first of all, we can see all the angles are congruent. Now, for them to be similar, the sides must also be proportional. So what we're going to do to check that is we're going to set 1 to 2, the angle with one arc to the angle with two arcs, AB, is 15, and we're going to put that over the angle with one arc to the angle with two arcs, which would be FE, 15 over 20, and see if that equals 2 to 3, which would be 12 BC over 2 to 3 ED, which is 16, and see if that equals 1 to 3, which would be 18 over 24. Now let's reduce our fractions and see if they're equal. This reduces to 3 over 4, this reduces to 3 over 4, and this reduces to 3 over 4. So, since our angles are congruent and our sides are proportional, 3 to 4, the triangles are similar. So now we write our similarity statement. We're going to say triangle A, B, C is similar to triangle, now make sure you match up the corresponding vertices. F has one arc, E, D. Any other order, you're going to miss it. Make sure you match up corresponding vertices. A corresponds to F, B to E, and C to D. And last, our similarity ratio, which we already got, is 3 to 4. Quick check number 2, ask us to sketch a couple triangles and then try to determine whether those triangles are similar or not. So please pause the video while you try to do this. Here I've sketched the two triangles. Now I'm going to mark the corresponding angles congruent. It says angle X is congruent to angle M, angle Y congruent to angle N, and angle Z congruent to angle P. Alright, so all our angles are congruent. Now we just have to find out if our sides are proportional. To see if our sides are proportional, we're going to put 1 arc to 2 arc, xy over mn, and see if that equals, question mark, see if that equals yz over np, and then see if that equals xz over mp. And since all of these fractions reduce to 2 over 3, then the triangles are similar. So first we're going to write a similarity statement. Triangle XYZ is similar to triangle MNP with a similarity ratio of 2 to 3. Example number 3 tells us the two quadrilaterals are similar. LMNO is similar to QRST, and ask us to find the value of x. Well, of course, to do that, we're going to set up a proportion. All right, the top ON over the bottom LM has to equal x over 6. Then we simply do cross products. We're going to multiply 5 times x and 2 times 6 and divide both sides by 5. So x equals 12/5. Check number 2, they're asking us to find the value of SR, which I shall call y. Please pause the video while you try to figure out y. Again, we're going to set up a proportion. This time, I'm going to use the proportion 3.2 over y has to equal 5 over 6. And then, of course, we do cross products. 5y has to equal 6 times 3.2. So 5y equals, I believe that's 19.2. And then we're going to divide both sides by 5, which gives us 3.84, but since it asks us to round our answer to the nearest tenth, we would answer 3.8 for quick check number 3. We are going to go over example 4 and quick check number 4 in class together. So let's move on to the last page of lesson 7.2, page 375, which talks about the golden rectangle. A golden rectangle is a rectangle that can be divided into a square and a rectangle that is similar to the original rectangle. As you can see off to the right, they've taken a golden rectangle, broke it up into a square, and another rectangle. The remaining rectangle is a golden rectangle again, which can be broken up into a square and another golden rectangle, and which again can be broken up into a square and a golden rectangle, repeated times. Every time the rectangle is similar to the original rectangle. It says the ratio of the golden rectangle is called the golden ratio, which is about 1.618 to 1. It also talks about how pleasing the golden rectangle is to the human eye and how it has appeared in architecture and art since ancient times, and Leonardo da Vinci, who by the way lived to be 48, 58, 67 years old, 67 years old back in the early or late 1400s and early 1500s. To me, that's pretty amazing. I'm sure that would calculate out to be about 90 or 100 years old today. Anyway, he was a big fan of the golden rectangle and used that in his book called The Divine Proportions. Example 5 says, an artist plans to paint a picture and he wants the canvas for the picture to be a golden rectangle with the longer horizontal sides to be 30 centimeters. the longer sides need to be 30 centimeters. How high will the canvas be? We'll simply call that X, and we have to set this up in a proportion. As we stated previously, the ratio of the golden rectangle is 1.618 to 1. So if we want our canvas to be in a ratio of 30 to X, we simply set up the proportion 1.618 over 1, and that's got to equal 30 over X. We do the cross products, 1.618X has to equal 30 times 1. Divide both sides by 1.618, and we get the height of our canvas. To be approximately, X is going to equal approximately 18.5. Quick check number 5 asks us to find the length of a golden rectangle, find the longer side of a golden rectangle if the shorter side is 20. So, again, I'm going to draw a couple pictures. They always help me. The shorter side is 20. What's the length of the longer side? Again, the ratio of our golden rectangle is 1 to 1.618. So now, please pause the video while you set up a proportion and figure out the length of the longer side of this golden rectangle. I'm going to put 20 over X equals 1 over 1.618. And we do cross products, which gives us 1 times X to equal 20 times 1.618. So X equals 32.36. It did not tell us where to round. If we round this, X is approximately equal to, round it to the nearest tenth, 32.4. This concludes lesson 7-2.